Good morning all. So again this is the lecture 3 on Nano Materials, that is unit 5. So here we will again cover some contents of the nanotechnology. So again first we will see the introduction to nanotechnology, then some special topics in nanotechnology, that is single electron transistor, and to study the single electron transistor we should know the quantum dot. First we will cover the quantum dot and then single electron transistor. So as we have seen in second lecture that what is the nanotechnology. So nano is 1 billionth or 1000 million, that is 10 raised to 9, and that is very small. The nanometer is 10 to the minus 9 meters, and that is the thickness of the hair, right? That is 1 billionth of a meter. The nanoparticle is 1 millionth of multimeter, that is 1 into 10 raised to minus 6, and that is the size dependent property of the nanomaterial. So nanocrystal is a material particle having at least one dimension smaller than 100 nanometers and composed of atoms in either a single or polycrystalline. Introduction to again nanotechnology. So nanoalloy is an alloy consisting of dispersed nanoparticles of 2 or more meters. Nanoengineering is the practice of engineering on the nanoscale. It derives its name from the nanometer, a unit of measurement equivalent to 1 billionth of a nanometer, that is the nanoengineering. Then nanostructure is a structure of intermediate size between microscopic and molecular structures, and that nanostructural detail is microstructure at nanoscale. So nanodot is also one technology which uses nanometer scale localized structures. So nanodots generally exploit properties of quantum dots, that we'll see, to localize magnetic or electrical fields at very small scales. So applications for nanodots could include high density information storage, energy storage, and light emitting devices. So nanomedicine is the medical application of nanotechnology. Nanomedicine ranges from the medical applications of nanomaterials and biological devices to nanoelectronic biosensors, and even possible future application of molecular nanotechnology such as biological machines. Current problems for nanomedicine involve understanding the issues related to toxicity and environmental impact of nanoscale materials. So the materials whose structure is on the scale of nanometers, that is 1 billionth of a meter. So frozen organs could be brought back to life safely one day with the aid of nanotechnology, with improved tissue preservation using inductive heating of magnetic nanoparticles. Now quantum dot. So to study the single electron transistor, we must have a knowledge of quantum dot, right? So what is a quantum dot? So quantum dot is a nanoparticle having all the dimensions reduced to below 100 nanometer, which is the main building block of single electron transistor. And single electron transistor is same to that of our basic transistor, and that is thrill effect transistor. I think you have studied that in basic electronic subjects and power electronics, right? So this single electron transistor is actually a new type of switching device that uses controlled electron tunneling to amplify current. So transistor is what? It is basically a switching device, and that is used to amplify the current. Right? Similarly here the single electron transistor is used for quantizing the electrons and to amplify the current, right? So when all the three dimensions of a material reduce to the nanometer range, then this material is called quantum dot. So what is a quantum dot? Quantum dot is that when all the dimensions of the materials are reduced and that are reduced to the nanometer range, then that material is called quantum dot. So the shape of that quantum dot may be cubical or spherical. So when the material dimensions reduce, then the delocalized electrons become localized and confined with discrete energy levels, which can be called quantized, right? Means what? whatever the material is there, and when it gets reduced in size, and that is to the nanometer range, then whatever the electrons present in that material which are delocalized, then that become localized, and whatever the energy is there, that is discrete energy levels, and that's why we can say that the electrons are quantized, right? So as such they behave like an atom, and therefore sometimes referred to as artificial atom. So when the material gets reduced, then their properties will change, right? So that's why its electrical and optical properties depend mostly on its size and geometrical structure of the quantum dot. So quantum dot is very important here to study the single electron transistor, because the material gets reduced, and due to that the properties, electrical and optical properties changed, right? And that depends on the size and geometrical structure of the quantum dot only. So there is metallic and semiconductor quantum dots. So the metallic quantum dot used in the construction of single electron transistor, right? So which dot is used here? Metallic quantum dot. So the density of quantum energy states of localized electrons depend on the size of quantum dot. So the smallest quantum dots have the compressed quantum energy states, whereas the biggest quantum dots have spaced quantum energy states of localized electrons, as described in the figure below, right? So here it is clear from the figure A that the whatever the quantum dots are there, that are having the compressed quantum energy states, and in the figure B, whatever the quantum dots are there, that are having the spaced quantum energy states of localized electrons, right? Now the single electron transistor. The concept of miniaturization originated after the deliberation of a talk given by physicist Richard Feynman on the 29 December 1959, and that led to the development of quantum dot, which is the basic building block of single electron transistor, and is a new type of switching device used for controlling the tunneling of electron to amplify current. So according to Moore's law, single electron transistor may be alternative of complemented metal oxide semiconductor, that is CMOS device for the next generation electronic devices and sensors. So whatever the talk is deliberated by the scientist Richard Feynman, then in his talk he challenges the miniaturization and focuses idea on how to manipulate and control the matter in atomic and molecular levels. So his dream come true into reality with the discovery of carbon nanotube by Sumio Iijima in 1991 at the NEC laboratory, Tsukuba, Japan. So this discovery became the launching pad of today's nanoscience and nanotechnology. And then the worldwide scientists, researchers, engineers and nanotechnologists have started to investigate a variety of ways to synthesize materials in the size of nanometer, and finally led to the development of quantum dot, and which is the building block of the single electron transistor, right? So, so the single electron transistor is expected to be an option to replace normal transistor, either bipolar transistor or field effect transistor. So the building block of computers for the next generation of electronic devices like optical computers, etc. However, the single electron transistor is yet in its infancy because of complexity and cost effective fabrications, but still having promising applications in the next generation electronic devices and sensors. So the here what is our main aim is that the fundamental understanding on operation of single electron transistor and its promising applications in the alternative devices to meet the upcoming challenges for further miniaturization and reducing the power dissipation, right? So the single electron transistor is same to that of the bipolar junction transistor and field effect transistor. So the what is meant by transistor? That which has three parts, right? So this was integrated in a chip in an integrated circuit in 1961. So in 2003 it was reduced to a processor consisting of millions of transistors in a chip to be used in a computer. So finally the processor size became 22 nanometer by the year of 2013. So as such, miniaturization of transistor has made further complemented metal oxide semiconductor as the workhorse of modern electronics. So by the forecast of Muir's law as depicted or as discussed, so CMOS, that is complemented metal oxide semiconductor, has attained its least most possible size and likely ending the regime of semiconductor technology, right? So the single electron transistor is basically similar to that of the bipolar transistor or field effect transistor. Now we'll see the construction of single electron transistor, and we know that it is a new type of switching device that uses controlled electron tunneling to amplify the current. So this transistor is constructed based on quantum mechanical principle, and the single electron transistor is similar to the normal field effect transistor except that the channel is replaced by quantum dot. So as we know that in transistor there are the three basic parts: source, gate and drain. So similarly here there are the source, drain and gate as shown in the figure, right? But the basic difference is that the channel is replaced by the quantum dot. Okay, so the quantum dot is separated by thin insulators from both the source and drain, and that's why the gate is connected to the quantum dot by capacitor Cg as shown in the figure. So in a single electron transistor, electron tunnels in two states such as shown in the figure, from source to dot and from dot to source, right? So the gate voltage Vg controls the charge on this capacitor Cg. That's what is the function of voltage Vg here. It is used to control the charge on the capacitor. Now the working principle. So the metallic quantum dot, which is separated from the source and drain by the thin insulators, is capacitively coupled to the gate as shown in figure C, right? So this gate controls the tunneling current across the tunnel barrier and operates on the principle of Coulomb's blockade. So the energy needed to charge the capacitor is E raised to 2 by 2, and it is typically 80 milli electron volt. If this energy is not supplied to the system, electron transport will be blocked at sufficiently lower temperature, right? And this is known as Coulomb blockade, right? So it is shown in the figure B. So what it means that whatever the energy is supplied, right, and that is not supplied to the system electron, then the electron transport will be blocked at sufficiently lower temperature. So it is clear from this characteristics that when if the temperature is low, then the electron transport gets blocked, right? And that's why it is known as Coulomb blockade. And from it is clear that the source and the drains are separated by a thin insulator with the help of quantum dot, and that's why the electron tunneling is from source to drain and source to quantum dot and quantum dot to drain, right? And that will control the tunneling electron across the tunnel barrier, and that's why to control the charge on the capacitor here the voltage V is used. So here battery V is used to give the supply or to give the source to the transistor, right? Now the working principle, and to study the working principle, first we must know the concept of biasing and what is meant by Fermi level. So the concept of biasing, that is related to the forward bias and reverse bias, or under no any source connected to the device, right? Now what is my Fermi level, and that we already discussed in lecture 1, that the Fermi level is covered in energy bands, and energy bands in a semiconductor are of two types. That is one which is filled with the electrons known as valence band, and while the other which is empty is termed as conduction band, right? And the gap between the two bands is called the band gap. So what is then Fermi level? So the Fermi energy level is the energy position within the band gap from where a greater number of carriers that may be different, that may be holes in p-type and electrons in n-type. So what is the Fermi level? So Fermi energy level is the energy position within the band gap from where a greater number of carriers that may be holes in p-type and electrons in n-type get excited to become charge carriers, right? So first, now we'll see what is the working principle under bias condition of single electron transistor. So under no bias condition, the transportation of electrons means what? The flow of electrons from source to drain, right? Source to drain, as shown in figure, that from source to drain will not take place. Why? It will not take place due to the Fermi levels, and the Fermi levels of both the source and drain is at the same level, and the localized quantum electrons are in quantum mechanically confinement and the discrete energy levels, and that's why the further transportation is blocked, and that is what uh, column blockade in quantum dot. So from it is clear that in the quantum dot the further transportation is blocked, right? So that is the condition under no bias. Got this? So due to the Fermi level, whatever the further transportation of electrons should happen from source to drain, and that is not happened due to the same energy levels, right? Means whatever the holes present in the p-type and whatever the electrons present in the n-type materials, that are at the same energy levels. So there should be some difference, right? And that difference is happened when we give the supply or source to the device, right? So this is the condition under no bias. Now under biased condition. Now if a bias voltage applied between drain to source, then the Fermi levels of sources S will go up and of drain T go down by the amount of energy divided by 2, which cause of Fermi levels between source and drain. So this situation is depicted in figure, right? So from figure it is clear that whatever the charge carriers are there in the source, that are more, and whatever the charge carriers are there in the drain, that are less. So there is a what? Gap in the energy levels, right? So Fermi level is different, Fermi energy level is different, and that's why it is possible that electron may transfer from source to quantum dot but without gate voltage, right? So it will not happen because for extra electron. Means what? That whatever the electron gets transferred from source to quantum dot but without gate voltage, and it will not happen because for an extra electron. Getting this? Right? So from figure it is clear that the electron transfers from source to quantum dot, right? And there is no any voltage given to the gate, right? And if there is no any extra electron, right, then it will not happen, and the energy of the quantum dot will be increased by the same amount, which is contrary to the principle of conservation of energy of the system. So as such, by sweeping the gate voltage for a fixed drain to source voltage, that is VDS, the tunneling of one electron through the quantum dot in a fashion source to quantum dot and quantum dot to drain is possible to make. So here it is clear that when we give a supply to the transistor, that is single electron transistor, then the transfer of electron may happen from source to quantum dot, but there is no any need of voltage given to the gate, right? And if there is no any extra electron, right, then the energy of quantum dot will be increased. Okay, so that is the difference under the bias and under unbiased condition, right? So biased means what? We are giving supply to the transistor. Now the third condition is that when the voltage is given to the gate, right? So when a gate voltage, that is Vg, is changed by some value, then for a certain situation the whole energy levels of quantum dot go down, as shown in the figure, below the Fermi level of source region but remain above the Fermi level in the drain region. Right, it is shown in the figure. So under this condition, electron from source will hook to the quantum dot and from quantum dot to drain. Right. So what is the flow of the electrons? It is from source to quantum dot and quantum dot to drain. Why? Because it is from higher potential to lower potential. Then accordingly the laws of conservation of energy will be maintained inside the quantum dot. So it is clear that the gate controls tunneling of one electron from source to drain. So this is the working principle of single electron transistor. And it can also be cleared from by the characteristics. So if a curve for drain current I as a function of gate voltage Vg is plotted, then the current spike will be obtained even after some value of voltage as shown in the figure A, right? So there are the spikes of the current versus the gate voltage. So for different gate voltage, by changing the bias, whatever the voltage is from drain to source, then the current I will increase. That is shown in figure B. Right here, the CB is what? Common base configuration, and VDS is what? The voltage from the drain to source, right? And due to that, the current will increase. So if both the bias is simultaneously changed and plot the data as VDS versus VG, right? The voltage to drain and source and gate voltage, then the column diamond will be obtained as shown in figure C. Means what? When we take the two parameters on the x-axis, that is gate to voltage source, right? And drain to source, then the diamond shaped is formed, and that is known as column diamond. Now once the construction working principle is known to us, then we can easily know the applications of any device. Now the applications of single electron transistors. So it is used in a variety of applications, and first one is that it is efficient charge sensor for reading out the spin or charged qubits confined in quantum dot. So the single electron transistor can be used as an efficient probe of signal to noise ratio, both for DC and radio frequency single shot measurement. Then the second application is that it is used to detect the infrared signal at the room temperature and therefore can serve as IR sensor in sophisticated device like IR camera. Then next is can be used as a extremely sensitive and potentially useful detector of microwave wave radiation. Then due to the high sensitivity of single electron transistors, it enables to be used as a super sensitive electrometers in unique physical measurements. Then another application of single electron electrometry is the possibility of measuring the electron addition energies and hence the energy level distribution in quantum dots and other nanoscale objects. Right? So the problem of leakage current is solved by the use of another logic device named charge state logic, in which single bits of information are represented by the presence or absence of single electrons at certain conducting islands throughout the whole circuit. So in these circuits, the static currents and power vanish since there is no DC current in any static state. So and state, that is single electron transistor having non-volatile memory function, is a key for the programmable single electron transistor logic. So one new avenue toward a new standard of absolute temperature can be developed by the use of single electron arrays. So the single electron transistors can be used in the hold state mode. So these are the some applications of single electron transistor. Now we see the limitations. So despite of variety of applications, single electron transistor implementation in the device has some limitations, and that are as follows. The first major limitation with the single electron logic circuit is the randomness of the background charge. Then outside environment linking with single electron transistors by normal wire connection is another limitation considering the size of SCT. Now lithography technique is another major limitation in single electron devices because of difficulty in fabrication at room temperature. Then the rate of coherent quantum mechanical process is crudely less than that for the single electron tunneling. Okay, so this is the single electron transistor. So if you have any question, then please put that in discussion forum on each platform, right? So thank you all.